Hello, in this video I am going to be demonstrating through a few examples how to find the nth term of a sequence, sometimes referred to as the general term of the sequence. So let's get started. In this first sequence, we want to look at the fact that each one of these terms has a common difference. So what I usually look for first is for an arithmetic sequence. An arithmetic sequence. An arithmetic sequence, the difference between each two terms is exactly the same. And you'll notice that the difference between each term here is 3. So the difference is 3. We also want to know what the first term of the sequence is. The first term is 5. From there, the general form of an arithmetic sequence is a sub 1 plus the common difference times n minus 1. So just plugging these things in, we have a sub n is equal to the initial term 5 plus the common difference 3 times n minus 1. And then simplifying it. 5 plus 3n minus 3, or 3n plus 2. So that would be the nth term, or the general form of this sequence. But let's test it. Let's test a few points. Let's find out what a sub 1 is. A sub 1 should be 5. So we have 3 times 1 plus 2 is 5. The second term should be 8. A sub 2 is 3 times 2 plus 2, which is 8. And the third term should be 11. A sub 3 is 3 times 3 plus 2, which is 11. So it looks like we nailed it on this one. This is an arithmetic sequence. And I always look to see if a sequence is arithmetic before I look for anything else. The second thing that I generally look for in a sequence is if it is geometric. If it is a geometric sequence. And so here's an example of a geometric sequence, a simple one. These are going to be fairly simple examples. This is geometric because if we take the ratio of each term to the term before it, 4 over 2 is 2, or 8 over 4 is 2, or 16 over 8 is 2, etc., etc. The ratio of any two successive terms is constant. We have a constant ratio, which is going to be r. So the general form for a geometric sequence is a sub n is equal to a sub 1 times r to the n minus 1. In this particular case, r is equal to 2, and a sub 1 is also equal to 2. So plugging those in, we would have a sub n is equal to 2 times 2 to the n minus 1 power. Well, let's just test a few points again, just like we did with the last problem. So a sub 1 should be 2. Let's see if this works. We have 2 times 2 to the n minus 1 power, and when n is 1, we get 1 minus 1 is 0. 2 to the 0 is 1 times 2 is 2. A sub 2 is 2 times 2 to the 2 minus 1, which is going to be 4. And a sub 3 is 2 times 2 to the 3 minus 1, which will be 8. So it does seem to work just fine. So the general form, or the nth term, is this. So those are the first two things I look for. Is it an arithmetic sequence? Is it a geometric sequence? Another thing that's nice to look for is if you have a sequence such as this, where you have alternating signs. This is called an alternating sequence. And the signs could be alternating negative positive or positive negative. Generally speaking, a sub n is going to be some power of negative 1. Because when negative 1 is raised to an even power, we always end up with a positive 1. When negative 1 is raised to an odd power, we end up with a negative 1. So we're going to end up with a sub 1 is negative 1 to n in this particular case, because when n is equal to 1, we want the outcome to be negative. So negative 1 to the first power is going to be negative 1. So let's try it. A sub 1 is negative 1 to the 1 is negative 1. A sub 2 is negative 1 squared, which is 1. A sub 3 is negative 1 cubed, which is negative 1. Now, what if the signs were different? What if it was positive, negative, positive? Well, then we would still want a negative 1, but because we want the first term to be positive, we could simply add 1 to that. And so we could subtract 1. We could see that it would work either way. Or, in this particular case, n minus 1. So let's just see the first term. A sub 1 is going to be negative 1 to the 1 plus 1, which is 2. Negative 1 to the second power is 1. Or negative 1 to the 1 minus 1 is 0. And anything raised to the 0 power is 1. So we're going to get a positive 1 either case. And so this is how we deal with alternating series. Sometimes you're going to have a series that looks like this. Something like 1, 4, 9, 16, 25. In this particular case, it would appear that all of these are perfect squares. And so it's important to identify each perfect square with the n number. So this is n equals 1. This is 4 is associated with n equals 2. 9 is associated with n equals 3, n equals 4, n equals 5, etc. So in this particular case, the output is the square of the input. Remember, the inputs are the integers 1, 2, 3, 4, 5, and the terms of the sequence are the outputs. So in this case, we simply have our n squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So sometimes it's helpful to look for little patterns like that. All right, now let's kind of put some of these things together to take a look at a little bit more difficult type of a sequence. Something like this. Negative 1 over 2, 4 over 7, negative 8 over 12. I'm sorry, that's negative 9 over 12, 9 over 12, 16 over 17, and then negative 25 over 22. So when you have something involving fractions, what I like to do is I like to look at the numerator and the denominator separately. Think of the numerator as its own sequence. Think of the denominator as its own sequence. And let's start by considering the fact that there is an alternating sequence. You have an alternating sequence here. So let's get that out of the way. To deal with the alternating sequence, we have a negative, positive, negative, positive. So I'm going to just want to be throwing in a negative 1 to the n into the sequence. I know I have that. And now if I consider the numerator, forget about the negatives. Just consider everything as positive. The numerator, we have 1, 4, 9, 16, 25. Well, that looks familiar. In this particular case, the numerator is simply n squared. And the denominator, if we look at the denominator separately, we have 2, 7, 12, 17, 22. And you'll notice that this is arithmetic. So since the denominator is arithmetic, we have to find the arithmetic sequence for that. So a sub 1 is 2. The common difference is 5. So a sub n is going to be 2 plus 5 times n minus 1. And so that's going to become 2 plus 5n minus 5, or 5n minus 3. So let's put all of this together now. Our a sub n, now remember, this is just the a sub n. This is just for the denominator. So we're going to have a negative 1 to the n. We always like to put that first. Then in the numerator, we have n squared. And then in the denominator, we have 5n minus 3. And there we have it. And we could check a few of these just to make sure that they worked. So let's do that. Let me check a sub 1. A sub 1, so we're going to have negative 1 to the n. That's going to be negative. So we're going to have a negative. And then we have n squared. So I'm looking over here at n squared. So I'm taking this and going up here now. So a sub, so what are we doing? N squared. So 1 squared is 1. In the denominator, we have 5 times 1 is 5 minus 3 is 2. And that's what we want, negative 1/2. A sub 2 is going to be positive. Negative 1 squared is positive 1. 2 squared is 4. And in the denominator, we have 2 times 5 is 10 minus 3 is 7. And finally, a sub 3, we have a negative 1 to the third power is negative. 3 squared is 9. And in the denominator, 5 times 3 is 15, minus 3 is 12. So it works for the first 3 terms. I'm going to go with that and say that we have got this correct. All right, let's just do one more. In this one, we have one more little interesting thing to do. Start off with 1, and then a negative 8 over 9, then 13 over 27, then a negative 18 over 81, and then 23 over 243. Okay, so let's consider each of these pieces separately. So first of all, we have an alternating series, and it starts with a positive. So I'm going to start with a negative n to the n plus 1. So when n is 1, we have a negative 1 to the second power, which is positive. Then it'll be negative, positive, negative. Now, in the numerator, if you just skip the first term for now, the numerator, if you eliminate the negatives and just consider them positive, the numerator, what do we have? We have 8, 13, 18, 23, and it appears that this is arithmetic. We have a common difference. So there is a common difference of 5, but be careful. What is a sub 1? A sub 1 is not 8. It is the 1. But that doesn't fit into the rest of the sequence. However, sometimes it's helpful to rewrite 1 as a fraction. So we could rewrite 1 as 3 over 3. Would that be helpful? Well, that would mean the first term of the sequence was a 3, and there is a difference between 3 and 8. There is a difference of 5. So a sub 1 is 3. Now we have a denominator to play with down in the denominator as well. And so we have a sub n is going to be equal to 3 plus 5 times n minus 1. A sub n is 3 plus 5n minus 5 or a sub n, is equal to 5n minus 2. So we have a 5n minus 2 to put in the numerator. Now let's consider the denominator. In the denominator, we have the numbers 3, 9, 27, 81, 243. Well, this strikes me as all being powers of 3. Powers of 3, 3 to the first, 3 to the second, 3 to the third. In other words, this is actually geometric. This is actually geometric. So with the first term, we basically have 3 to the first power. Then the second term, it's 3 to the second power. So it's going to be 3 to the n, which is geometric. If you take each term, 9 divided by 3 is 3. 27 divided by 9 is 3. 243 divided by 27 is 3. Okay, so the first term of this, for being a geometric, the first term of the geometric is 3. So we have a 3 times 3 to the n minus 1 to write this in the correct notation. Now notice that this ends up being the same thing. We're using the correct version. So 3 to the n, is that equal to 3 times 3 to the n minus 1? Because this is the correct form of a geometric, but this is basically what my series is. Well, if we let n be equal to 1, we have 3 to the first is 3. Over here, when n is equal to 1, we get 1 minus 1 is 0. 3 to the 0 is 1 times 3 is 3. And so it does work, and it'll work when n is equal to 2. So we can write it like this. We could also write it like this. We'll end up with the same thing. All right, let's put all of this together. So my total sequence is going to have a negative 1 to the n plus 1. And then we are going to have in the numerator a 5n minus 2. And then in the denominator, we have 3 times 3 to the n minus 1. All right. Now, there are different ways that you can algebraically play around with these sequences to make them look a little bit differently. As an example, I had mentioned earlier that instead of n plus 1, we could use n minus 1. Then you have a negative 1 to the n minus 1 and a 3 to the n minus 1. Could you combine those? Something to consider algebraically. All right, that is it. I hope this was helpful and that you will never have difficulties determining the nth term of a sequence again.